Thank you. So I gave you guys an extra day with the test. I was going to email it to you tonight, but I decided to email it last night. So it's going to take you some time to do it. So don't take the questions too lightly. They're fairly time consuming. So, but I tried to give you reasonable enough information so that it was, it could be done. All right. So we're going to continue on with our derivation of different methods for solving optimal control problems, pseudospectral methods. So if you remember, the problem that we were dealing with was the cost function was phi of x of plus 1. The dynamics were x dot equals f of x and u with an initial condition x of -1 equals x0. Now today what we're going to talk about is we're going to talk about using Gauss points. I was going to do Redal points, but I'm going to do Gauss points because it's the other extreme. So last lecture we talked about Lobato points. Today we're going to use Gauss points. So Legendre-Gauss. So discretization using LG points. Now, one of the things you got to be, this is a schematic that I alluded to at the end of last class, but I'm going to be a little more explicit. If you look on the interval -1 to 1, the Gauss points look like this. They cluster. This is tau equals 0. They cluster like this. I'm just doing this for I'm doing this for some set of points. I did it for an even set of points. If you do an even set of points, there are no points at the origin. If you do it for an odd set of points, then the middle point is actually always at the origin because they're symmetric. All right, now if you look at the LG points, the first LG point is greater than -1. The last LG point is less than +1. So clearly, if I'm going to use the Gauss points, and so let's write this, tau 1, which is the first LG point, is greater than -1. Tau sub n, which is the nth LG point, is less than +1. And I have n Gauss points, right? So n is the number of Gauss points. So if I'm going to do this with Gauss points, I have a problem on my hands, right? Because the boundary conditions, or the boundary points, are tau equals -1 and tau equals +1. But I have a set of Gauss points that don't include the endpoints. If I do what I did with Lobato, where let's just take this thought, okay? This is completely a thought experiment because this is the wrong way to do it. If I take the n Gauss points and I do the exact same thing with them as I did with the Lobato points. What did I do with the Lobato points? I constructed a state approximation that included all the n Lobato points, right? I then differentiated that state approximation, and then I collocated the result at the n Lobato points, right? N LGL points. And I showed you that when you do the state approximation, because you're using n points, you have a polynomial of degree n minus 1, because you're representing it as a summation of a bunch of n minus 1th degree Lagrange polynomials. So my state approximation is a polynomial of degree n minus 1. Its derivative, therefore, is a polynomial of degree n minus 2. And I collocated the result at n points. But I know that a polynomial of degree n minus 2 is uniquely determined by n minus 1 coefficients. So therefore, I'm overcollocated by one equation because I have one more condition than I need. and that differentiation matrix was singular, right? It's square and singular. If I do the same thing here, except for I just switch from Lobato points to Gauss points, I've made the problem worse because I now have n Gauss points. I go through the same argument. I collocate at the n, I approximate at the n Gauss points. I got a polynomial of degree n minus 1. Differentiated a polynomial of degree n minus 2. Collocate that at the n Gauss points. I have the same problem. I've got an overcollocated system, right? So that's the first problem I've created. The second problem I've created is notice that the first and last Gauss point are not at -1 and +1, right? So as a result of that, if I was to enforce the boundary conditions, or the initial condition at the first Gauss point, I'm enforcing it at the wrong point, right? Because it's not at tau equals -1. The boundary condition is at tau equals -1. That's not where the first Gauss point is. So the first Gauss point is the wrong place to enforce the boundary condition. The Mayer cost, similarly, is computed at the final point, +1, and +1 is not one of the Gauss points either because the final Gauss point is strictly less than +1. Now, one could make the argument, again, notice I'm not writing any of this down, okay? So there's a reason why I'm not writing any of this down. It's because I don't want you to write it down, because you're going to write it down and you're going to say, oh, he told me to do this. No, I'm telling you not to do this, which is why I'm not writing it down, all right? If you take these Gauss points and you keep increasing the value of n, what happens is the points, you get more and more points that cluster towards the ends of the interval, and each Gauss point, each endpoint Gauss point, so the first and last Gauss point, successively get closer to -1 and +1. So in the limit, as n goes to infinity, the first Gauss point approaches -1, the second Gauss point approaches +1. So you could make the argument, again, notice I'm not writing all this down, right? You could make the argument that if I just take enough Gauss points, my first and last Gauss point get close enough to -1 and +1 that I'm effectively at -1 or +1, right? Well, it still doesn't change the fact that doing it this way, you wind up with a singular differentiation matrix. So you're still applying the boundary conditions at the wrong point, even though, yes, they're getting closer and closer to the correct values of tau, but you're doing that in conjunction with the fact that you're doing this with a square and singular differentiation matrix. So the whole thing just doesn't make any sense. So how are we going to use Gauss points? Because we've got this problem here. We got n Gauss points, neither one includes the boundary. So what we do is this, is we introduce, by the way, we introduce the following non-collocated points. And this, by the way, is a, so we say tau 0 is equal to -1, and I'm going to introduce tau n plus 1 is equal to +1. Okay, now I'll show you how to use this in just a minute. By the way, I really can't take credit for this. This was David Benson's 2004 MIT PhD thesis. Dave and I are very good friends, and I was on his PhD committee, and he was when I worked at Draper, and he was just this is a brilliant piece of work. I mean, I kid you not, this is probably one of the best pieces of work to come out of any PhD thesis that I have ever read in my life. I mean, Dave is brilliant, and he figured this out. And when he did, it's a profound result because it's so profound that making this switch, it looks like you're not doing anything, but by making the switch the way I'm about to show you, it's baffling how it actually comes out. And it doesn't just come out to look nice. It actually is mathematically completely correct. And it's just a beautiful thing. So here's what we do. What we're going to do is we're going to include tau 0 in the state approximation. So the state approximation is going to look like this. Now, so I should actually be a little more careful here. This is x of tau is approximated by capital X of tau. Now, if you look at that, you say, well, that doesn't look any different. I mean, it just looks like you just kind of like it's like like a magician with a rabbit in his hat, right? I mean, it just basically all I did was I changed. I'm going to put this as an aside. You don't write this down. I'm just going to put this over here. Remember for LGL, the summation x of tau was equal to the sum from I equals 1 to n of xi li of tau. Okay? You don't have to write this down. I just put that there as an aside. So if you look at this, you say, well, that just doesn't look any different, right? Because here I have a polynomial of degree n minus 1. I'm using endpoints, right? Here, what do I have? I have a polynomial of degree n, and I'm using n plus 1 points, right? Because I'm summing from 0 to n, right? So, and my tau 0 is equal to negative 1. So what have I done for myself? I've done nothing, right? I've added a point, and I've added a degree to the polynomial. So I'm winding up in the exact same place I was over here, right? I couldn't have done anything. But now watch. This is what happens when you do this. So I'm going to erase this aside because it's going to get in my way. And it's a strange result in some ways, but it's not that strange. So what's x dot of tau? It's the sum from I equals 0 up to n of xi li dot of tau. What's the degree of this polynomial? I just said it. What is it? It's an nth degree polynomial. Right? I'm using a basis of nth degree Lagrange polynomials. So what is this? This is an n minus 1th degree polynomial. So if this is an n minus 1th degree polynomial, how many coefficients do I need to uniquely define an n minus 1th degree polynomial? N, right? So in order to uniquely define this polynomial, we need n points. How many Gauss points do I have? How many Gauss points do I have? I have n Gauss points. Right? Because these are the n points on the interval negative 1 to 1, but they don't include either of the n points, right? So because they don't include either of the n points, I have n interior points that form the values for my quadrature. My quadrature is going to be done using those points. So these are my points. But what I've done in the state approximation is I've added a non-collocated point into the state approximation. So I started with a polynomial of degree n. I didn't start with a polynomial of degree n minus 1. I started with a polynomial of degree n, differentiated it, got a polynomial of degree n minus 1, which is uniquely defined by n points. But I have n points. I have n uniquely defined quadrature points. And I said, remember at the beginning, that all the quadrature points must be used for collocation. Remember I said that last lecture. So these methods are designed so that I have n quadrature points. Remember in the Lobato case, I also had n quadrature points, right? Here I still have n quadrature points. It's just that they don't include either of the n points. So now let's look what happens. Now let's suppose we collocate x dot of tau at the n Legendre-Gauss quadrature points. Okay, so here we go. Here's what we're going to do. We're going to take x dot of tau j is going to equal f of xj uj and this goes from j equals 1 up to n. So this says that the sum from I equals 0 up to n of x I li dot of tau j is equal to f of xj u j. Okay, now, if you look at this equation, you'll see that how many of these do I have? What is j runs from 1 to n, right? So I have n vector equations, right? I have one for each value for each Gauss point. But I'm using a basis of Lagrange polynomials, my original Lagrange polynomials. I have n plus 1 Lagrange polynomials. So the original Lagrange basis that I've got, Li dot of tau, is a product from j equals 0 up to n, j is not equal to I, of tau minus tau j, all divided by tau I minus tau j. So if you look at this, you'll see that each of these is a polynomial of degree n, right? But I'm using n plus 1 points, but then each one of them knocks off one entry because j can't equal I in that polynomial. So I got a polynomial of degree n. If you look at that, you'll see that the number of points that I have on this side, meaning the number of values of the state I have on this side, is not the same as the number of values of the state I have on this side, right? On this side, how many different values of the state and the control am I using? N, right? Because I'm doing this for j goes from 1 to n, right? Over here, my summation goes from 0 to n. So that means that the state approximations here run from x0 up to xn, right? But x0 is the value of the state at -1, right? So x0 is the approximation of the state at -1. And then xj are the approximations at the state at the n LG points. And this is j running from 1 up to n, which means that the left-hand side, so the left-hand side uses n plus 1 values of the state approximation. Or I should say it a little bit differently. I should say uses the state approximation at n plus 1 points, where the n plus 1 points is equal to the initial point plus the n LG points. So you can see that I've got a discrepancy between these, right? Because if I had the same number of points on both sides, I would wind up in the same situation that I wound up with in Lobato, which is that I'm collocating at the same number of points that I'm using in the quadrature as the same number of points that I'm approximating, right? But I'm not doing that here. Here I'm using one more point in the approximation. So this matrix, so let's say Li dot of tau j, this is not a square matrix. In fact, it can't be a square matrix because look what happens. I runs from 0 up to n, and j runs from 1 up to n. So the number of columns of this matrix is what? I have j Gauss points, and I'm running I going from 0 to n. So how many columns do I have in this matrix? How many columns do I have? If you don't like it, we'll just write it out. I've got L0 dot of tau 0, Ln dot of tau 0, Ln dot of tau. Let's make sure I do this right. Yeah. L0 dot tau 0. No, I did this wrong. Sorry. I always get these backwards. So I goes from 0 to n, number of columns. Here. Yeah, no, this is right. This is right. And then L0 dot of tau n all the way up to Ln dot tau n. No, I did this wrong. There we go. Okay, the tau 1. So if you look at this, how many rows do I have? I have n rows. How many columns do I have? I'm going from 0 to n. How many columns do I have? N plus 1. So this is an n by n plus 1 matrix. So I can let d ij equal li dot of tau j. So that's the LG differentiation matrix. Okay, now, if you write that out in matrix form, we can do it this way. We can write this matrix as follows. Which is we can say that D, which is an element of R n by n plus 1, can be written as follows. D0 plus D, sorry, plus 1 colon n, where this is the first column of D, and this are columns 2 through n plus 1 of D. I mean, I'm going from 1 to n, but this is the first column, and those are columns 2 through n plus 1, right? So if I write this using that notation, and again, I do the same thing that I did before, where I say I'm going to let x equal x0 up to xn. Remember, these are all row vectors now. And as a result, x of 1 through n is just equal to x1 up to xn. Write it like that. Then what we get here is we get a system that looks like this. And I'll do one more thing just to make this complete. F of 1 through n is equal to f evaluated at x1, u1, all down to f evaluated at xn, un. Okay. So now that's what I've got. So if you write this, you see that the right-hand side only goes from 1 to n. So I get d times x is equal to f1 colon n. But this x is this one over here. It's not that one, okay, because it includes the initial point. So what I can do is I can rewrite this as this way. I could say d0, d1 through n times x0, and then I'll write x1 through n, let's write it this way, is equal to f of 1 through n. So now I can just do the multiplication there, and I get the following result. I get d0 times x0 plus d1 through n, x1 through n, is equal to f of 1 through n. Okay. Now, this is the reason why I chose row vector orientation for this, because the math works out if you do it this way. Now, Dave came up with this, and I'm sure I accord him the proper respect. I call him Dr. Benson because he's got a PhD now. So, but he's my friend, so I call him Dave. So, but anyway, the thing about it is, during the time that he was doing his PhD thesis, he made this empirical observation. This was the empirical observation he made, and he wasn't able to prove it at the time. I'll get to how it was proved later, but because it's been proved. But he made this observation. He said, suppose now, and I'm going to draw a line. Suppose now that we want to perform LG collocation, but using an integral form for the collocation. So we're not going to do this by differentiation. What I did up till this point was I did differentiation. I took the state approximation, I differentiated it, I got that result up there. So yeah, this is the key observation in this research, and this is the profound result, is that we have n LG points, none of which includes tau equals -1. So there is no point at tau equals -1 that's in this quadrature set. This quadrature set includes only points that are on the interior of -1 to 1. So let's suppose that I take the integral of the dynamics, right? I have x dot equals f of x and u. Let's suppose we integrate this. So I know that x of tau is equal to the integral from -1 to tau of f of x of s, u of s, ds. I haven't done anything fancy there. It's just an integral, right? I start at -1. I'm going to integrate to some point tau, right? Now, what the key observation is, suppose we integrate to each LG point. So what we get is we get x of tau I, well, let's do tau j, is equal to the integral from -1 to tau j of f of x of s, u of s, ds. Now, I haven't done anything there either. I just substituted in a particular value. Now, but j runs from 1 to n, and these are not just any tau j. Those are the Gauss points. So I'm going to integrate to each Gauss point. So if you look at this on the schematic again, if I draw the schematic, there's -1. There's the first Gauss point. So I'm going to integrate from here to there. There's the second Gauss point. I'm going to integrate from here to there. There's the third Gauss point. I'm going to integrate from here to there. And I'm going to keep doing that all the way until I get to the end, which is, oh, not enough room here, which is I'm going to integrate from here to the last Gauss point, which is right there. Okay? So this is the first, second, third, all the way down to the nth Gauss point. Now you'll see that in order to do that, I'm like, well, I'm missing some information, right? What am I missing if I integrate to the last Gauss point? Where do I need to evaluate the Mayer cost? At the boundary point, which is at +1, right? If I integrate to the last Gauss point, I don't have the information at the final point, right? Look at this equation up here. What am I missing in this equation? Remember, the indexing runs, 0 is -1, 1 through n are the Gauss points, and n plus 1 is this point that I haven't yet dealt with, right? This system of equations doesn't include the final point. So I have a problem on my hands because I have a system of equations that doesn't include a point that I need to evaluate the Mayer cost, or if I have a general problem, to evaluate the boundary conditions at that final point, right? So I'm missing some information. So the observation that Dr. Benson made is that I'm going to integrate to here. I'm going to integrate all of these. And in fact, what I'm going to do is I'm going to run from 0 to n plus 1. Sorry, 1 to n plus 1. First Gauss point all the way to the end. Right now, what he did was he said, well, each of these, this is really easy to deal with, right? Because I know that this interval can be transformed as follows, which is the integral from -1 to tau j can be transformed to the interval from -1 to 1 with a factor of tau j plus 1 over 2, because I just did a transformation in mapping s to the interval -1 to 1, and then doing the transformation. I wrote down that transformation last week. So what he did was he said, well, I can write this. X of tau j is equal to tau j plus 1 over 2 times the integral from -1 to 1 of f of some, x of, let's not call it s, let's call it zeta. Okay? So he said, well, I can do that. And now this can be approximated by a quadrature. I can approximate each one of these by a quadrature. So I get tau j plus 1 over 2 times the sum from I equals 1 to n, so now this becomes an approximation, of Wi Fi, where these are the LG quadrature weights. Now look what happens when tau, or j, such as j, is equal to n plus 1. When j is equal to n plus 1, I get 1 plus 1 divided by 2, which gives me 1, right? Which means the final point, I should actually be a little more careful here. There's a plus x of negative 1. Sorry, should be. I forgot the initial condition. Sorry. I always forget the initial condition. So if you plug in j equals n plus 1, just take that case. J equals n plus 1. What do I get? I get x of plus 1 is approximated by x of minus 1 plus this quadrature. So what this says is, it says that the final value of the state is equal to the initial value of the state plus the integral approximation from negative 1 to 1. Isn't that what it's equal to? Right? If I want to integrate to get to the end point, I start at the initial point and I approximate the integral across the interval. But the integral is approximated by Gauss quadrature. So this becomes the standard Gauss quadrature. So if you do this with the approximations in place, if you basically say I'm going to approximate all this with approximations, I get x n plus 1 is equal to x0 plus the sum wi times fi, or I should say f of xi ui, I equals 1 up to n. So I now have a way of being able to get that final point. Now let's do all the rest of them. So the next observation he said was, well, I'm going to do all of them that way, right? So what I get is, because I've got these factors of tau j plus 1 over 2 in front of this, what I get is I get xj is equal to x0 plus, now I'm going to lump into this, I'm going to put these all into quadrature form. I get alpha, and I get f, and I get I equals 1 up to n. And what I'm going to do is this is going to be alpha ij times fj. Sorry, fi. And if you really want to do this in the same order I did before, I'll flip the indices. So what I got here is alpha ji are the quadrature weights on negative 1 to tau j. Tau j happens to equal 1, then they're the standard Gauss quadrature weights. So now what I get is I take that alpha matrix and I string this whole thing into a system. Notice how many equations do I have here? I'm integrating this. I'm doing this integral approximation from 1 to n. So what I get is I get x1 up to xn is equal to this x0. So what I'm going to do is I'm going to form a column vector of 1s, multiply by x0, and then I get plus this matrix, alpha 1, 1, alpha 1n, alpha n1, alpha nn. This whole thing gets multiplied by f1 all the way up to fn. So now we take that approximation and we put it into a more compact form. So I'm going to let the alpha matrix, I'm going to call the alpha matrix, I'm going to call it, since it goes from 1 to n, I'm just going to call this whole matrix here, I'm going to call it A1 to n. So if you look here, see this is x1 to n, right? So what I get is I get x1 to n is equal to 1 times x0 plus a1 to n of operated on f of 1 to n. And I get this final equation, which says xn plus 1 is equal to x0 plus w transpose times f1 to n, where that's just a vector of those weights, of those standard Gauss quadrature weights. So now I've got all this stuff. Now let's take this equation and let's compare it to the equation I got when I did this in derivative form. So in derivative form, I got this. I got d0 times x0 plus d1 colon n x1 colon n is equal to f of 1 colon n. In integral form, what I got is I'm going to line this up so that we see this as clearly as I can. Well, I can't line it up. Yeah, can't line it up. I have to shift this over. Let me shift it over because I want to line this up. Okay. I'm going to write this over here. d0 x0 plus d1 colon n x 1 colon n is equal to f of 1 colon n. And now what I'm going to do is I'm going to put these here. So I've got x of 1 colon n is equal to 1. Line this up even more. I'm going to put this way over here. There's a reason why I'm doing it this way. Okay. Now let's look at these two systems of equations. So this derivative form and integral form. Okay. So this is the derivative form. This is the integral form. Now, the observation that was made, that Dave made in his thesis, is he says, well, this is a square matrix, right? So if this matrix could be inverted, if it was invertible, I could multiply this whole first equation through by that inverse, right? So let's suppose I do that. Suppose d 1 through n is invertible. So it's non-singular. If it's non-singular, I multiply through by its inverse. If I multiply through by its inverse, what do I get? I get d 1 colon n inverse times d0 times x0 plus x 1 colon n is equal to d1 colon n inverse times f of 1 colon n. So now all I've done is just multiply by the inverse. I haven't done anything fancy here. So if I rearrange this, I get x of 1 colon n is equal to, I pull this to the other side, minus d1 colon n inverse times d0 times x0 plus d inverse 1 colon n f of 1 colon n. Well, now that starts to look a lot like this down here, doesn't it, right? So if the following were true, if minus d 1 colon n inverse times d0 were equal to a column vector of 1s and d inverse of 1 colon n was equal to a of 1 colon n, what would be the result? The LG method would be a Gaussian quadrature method. Why would it be a Gaussian quadrature method? It would be a Gaussian quadrature method because I'm using the Gauss points, and I got the integral form by integration to each of the Gauss points, right? So because the integral form was obtained by integration to each of the Gauss points, and each of these sets of weights are Gauss quadrature weights scaled by this factor of tau j plus 1 over 2, it is a Gauss quadrature approximation to the integral to that particular point, right? So I've got n Gauss points, and if it turned out that when I did the derivative method, if I just inverted the derivative method by doing what I did here, if these things were actually equal to each other, my derivative method is actually an integration method, even though I didn't derive it that way. When I started by taking the state approximation. I added this initial point, tau equals -1, into the problem. I differentiated the result and collocated at the n Gauss points I got the same number of equations as I needed to uniquely define the polynomial of degree n minus 1. I needed n conditions. I have n conditions. So I said, well, that's a derivative method. That's what I got here. This was the last thing I did in the derivative form. But if I go the other way and I say, I don't want to do this with differentiation, I want to do it with integration, I wind up with this integral form. And if these things are true, then this is a Gaussian quadrature method. It's a Legendre-Gauss quadrature method, which you know is accurate or exact for a polynomial of up to degree 2n minus 1, right? So if this is in fact a Gaussian quadrature method, then that's true, which means these things have to be true. So I had another student, came along a few years later. Dave was at MIT. And so she was sitting there scribbling out all this stuff with Radal, which I haven't talked to you about. But we'll do that next class. And came up with these really weird observations that it looks like this matrix, if you invert it, is actually equal to that inverse. So her name was Divya Garg. She got her PhD last year. So she actually figured out that it turns out that if you construct these matrices in exactly this way, that the inverse of this matrix is in fact equal to this matrix, and this is the Legendre-Gauss integration matrix. So because this is the Legendre-Gauss integration matrix, because I got it by LG quadrature, then the inverse of this block of the D matrix, which are columns 2 through n plus 1, if I invert that, I wind up getting the integration matrix. So that was her long PhD thesis where she did all this stuff, and she included Radal and everything in here too. But she also proved, this is actually much easier to prove, but that the inverse of these columns multiplied by the first column, the negative of that is actually equal to 1. So it turns out that this Gauss quadrature method, or this Legendre-Gauss discretization, by including that initial point, is actually an integration scheme. It's a quadrature method based on Gaussian quadrature, and it turns out that it actually has this form. Now, it turns out that from a computational standpoint, and I'll get into computational issues a little bit later, this form is actually more efficient to use than the integral form is. But if I use this form, I'm actually doing the exact same thing as if I were using this form. So now I have the following set of equations. I actually can just leave it here, which is that I've got all the values of the state in this equation right here, except for the final value. But the final value is computed by Gauss quadrature. This is just a Legendre-Gauss quadrature approximation to the final value of the state given the initial value of the state. So now I have the state approximation at tau 0 all the way up to tau n plus 1, which means that I've covered both endpoints using LG quadrature. So the method, unlike the Lobato method where I had a singular differentiation matrix, these matrices are not singular. I have actually a full rank matrix in such a way that its inverse, the columns, if I lop off the first column, the remaining columns, the inverse, is actually equal to the matrix I would have gotten had I done this by integration. So I've preserved the fact that I'm doing integration even though I started with a state approximation and did differentiation. Now, that just seems kind of weird. You know, you're just like, well, that seems to kind of came out of nowhere, right? So if you look at this sort of in a cynical way, so there are people out there who are cynical. So if you look at this in a cynical way, or a way of, how do I say this? Of you didn't do anything different here. The key factor is you have this initial condition. And the initial condition must be separated out from the rest of the approximations. Because when you integrate a differential equation, you have to preserve the isolation of the initial condition. Because the initial condition doesn't affect the integral, right? If I have an indefinite integral, if I say I've got the integral of f of x dx, right? There's actually a constant that comes in there depending upon what the values of the initial conditions are, right? So that's what this is. That's the initial state. And that has to be separated out from the rest. Notice in all these equations, if I look over here, you see that this right here, see the initial state is separated out from the rest of them. See in this equation right here, The initial state is separated from everything else. So it's because I actually have an implicit integration scheme that I get to do this, right? And the quadrature points don't include either of the endpoints. So the one downside to Gauss, you see, you know how Dr. Banks says this. If you've ever taken one of his classes, he says that pain is conserved. All right, so there's pain in this too. All right, the pain is that the following, which kind of sucks, but you know what? That's why we're going to do the next lecture where we're going to talk about Redau. Because look at these equations right here. Where's the control approximated? I'm almost done. Control is approximation. The control approximation is done at these points, u1 all the way up to un. There is no control approximation at the initial point, right? Because f is being evaluated from 1 to n, right? So I'm never evaluating this right-hand side at any points other than the first to the last Gauss point. So that means there's no value of the control at tau equals -1, which is a problem because when you do control, you need the control, right? You need the control now. If I'm doing control, I want the control at the point that I'm actually starting to do the process of controlling, right? If I'm going to control from t to tf, I need the control at time t, right? I don't need it at some point into the future. Whereas the first value of the control here, u1, is at the first Gauss point, but the first Gauss point's not at -1. But -1 is my initial value, right? My initial value of time. So I'm actually getting the control only at the first Gauss point, which means I'm not getting it at the first value of time. So if I was going to do this, say, in a feedback sense, where I'm going to resolve this problem over and over again, I'm never getting the control at the endpoint that I want, which I'll leave that hanging for right now because we're going to do Redau next, okay? So that's it for Gauss.